All right, so I assume that we can get started. So welcome everybody to this session, no matter if you're coming from far away or just around the corner, like my colleagues here in Kingsoft. So just as usual, you can always ask questions on the QIP website in the chat feature. And also at the end of the hour, there will be a Q&A session on Zoom where you can also talk to the speaker. So, so this talk is by Zhao, and it's about Hamiltonian simulation with random inputs, and he's from the University of Maryland. So take it away.
Thank you very much. Thank you for your nice introduction. This is Zhao from QIP, Maryland. Today's talk is about Hamiltonian simulation with the random inputs. This is a joint work with Zhou, Alexander, Tongyang, and Andrew. Here is our archive number if you want to check it out. The Hamiltonian simulation or the quantum simulation is one of the most promising applications of quantum computers. This idea was first proposed by Richard Feynman in 1981. It's to use quantum computers to simulate the quantum systems. The quantum simulation can help us to solve the problem in the computational quantum physics, like to simulate the chemical reaction, condensed matter physics, or nuclear physics. Quantum simulation can also be used to implement other quantum algorithms, like a quantum walk, adiabatic optimization, or linear or differential equations. At first, let's give a formal definition of what is a Hamiltonian simulation problem. For a given Hamiltonian acting on n qubits, an evolution time t, and a predetermined accuracy or error epsilon, sometimes we can't have the direct access to the ideal evolution. It's the e to the minus rht. We have to construct some quantum circuits which are much easier to implement to approximate the ideal evolution with at most epsilon error. In a more physical or practical cases, we know our initial state. We may only care about some certain type of initial state, and we only want to guarantee that for this initial state, its output state is close to the ideal one. This is the second problem. For the first problem, a lot of effort has been made to estimate this error for different kinds of algorithms or different kinds of Hamiltonians. But for the second problem, the exploration is still limited. Okay. In the first problem, its error is the spectral norm of the ideal evolution minus the approximate evolution. It corresponds to the worst case input state. So that's why we call it worst case error. And using this worst case error analysis, we can guarantee that for any input state, your output state is close to the ideal one. But in practice, the real initial state, there are some states with a physical meaning, there are physical input states, like the low energy state, or some computational basis state, or some easily prepared state. But for the worst case input state, they could be far from this subsite. Then using the worst case error analysis, we overestimated the error and overestimated the required resource in Hamiltonian simulation task. Okay, in order to address this problem, recently people consider some specific setting, like the input state with a low energy and the input state with a fixed number of electron or spin. Moreover, we could also consider the observable, like the local observable or fixed observable, then they can help us to further improve the results. All this specific setting can help us to improve the performance in Hamiltonian simulation task. It means to reduce the error or reduce the required resource in this task. Okay, here we develop the theory of average performance from the input state from a given site or given example. We choose the state I with the probability pi, and the distance of output state can be quantified by different distance measures, like L2 norm or trace norm. And we can't solve this problem generally. We need some additional condition or assumption about this example. For example, we could assume that the states are uniformly chosen from the whole Hilbert space. It's called hard random state. But for this one, it's quite challenging to realize in practice. We could make it to a mild one, like a T design example. It means that for the T copy of some state, summation of T copy of some state can't be distinguished from the hard random integral. This is a T design. For the T design example, it also satisfies the T-1 design. So the 1 design is the largest site. It's the weakest assumption. The 1 design example is also much easier to realize. For example, consider the 0 state. Then we implement the single qubit random unit array on each qubit. This output state is a locally random state. This is a 1 design state. Another example is the uniform distribution over the orthogonal basis, like the computational basis. We choose the state 000, 001, or 1111. The computational basis state with the same probability. It's also a 1 design state. Okay, and at first I would like to give a brief summary about our main results. Here we mainly talk about 1 design example and the L2 norm. For the other type of the distance like trace norm, its analysis is similar. At first, we gave a general result for the average performance in Hamiltonian simulation. We related this performance to the Frobenius norm. And then we consider different kinds of algorithm like the product formula method, also known as Chorter method, and the Hamiltonian simulation algorithm based on the linear combination of unitary. It's RCU type. For the product formula method, the total gate complexity is the polynomial function of 1 over epsilon. But for the RCU type Hamiltonian simulation algorithm, its total gate complexity is the log function of 1 over epsilon. Here we just give a different error analysis. We will change or reduce this epsilon here. So because this log function for this RCU type algorithms, the total gate reduction could only be mild. So in the rest of this talk, we will just focus on the product formula method. If we are interested about RCU type results, you could read our paper. And we consider different kinds of the type of Hamiltonians, and we can have the different degree of improvement. And we also show an interesting destructive error interference in some special case. At last, we extend our result to a more general case. It's a random over subsystem problem. And this result can be related to the OTOC problem, can help us to reduce the error and the gate count in the OTOC problem. Okay, in the following, I will talk about this result 1 by 1 in more detail. At first, we want to know that the mean value is the summation of the square root of something. It's an L2 norm. And we can't directly estimate this one. So we have to use a Cauchy inequality at the first step. Then its up bound is the square root of the summation of something. And this up bound is related to the Frobenius norm of the multiplicative error. The multiplicative error here can be defined as follows. For the approximate evolution U, it equals the ideal evolution U0 times the identity plus the M. This M is multiplicative error. Okay, and a comparison in the worst case error analysis, the error is upbounded by the spectral norm of M. So it means that it's the largest eigenvalue of M. But in our case, in average case error, it's a Frobenius norm of M. It's a root mean square of the eigenvalue of M. Okay, that's the difference. And for this one, this Frobenius norm of M, and we also show that for the 2 design example, we can also upbound this variance. This variance is also upbounded by the function of Frobenius norm of M. If this Frobenius norm is very small, then according to the Chebyshev inequality, we know that for any input state, its performance should be close to the mean value with a high probability. So this implies that maybe the average case error analysis is a more representative quantifier in the quantum simulation task, right? And the Frobenius norm of this M highly depends on how you implement your approximate evolution. This one can be done by different kind of algorithm. The most widely used one is the product formula method. In this algorithm, at first we need to divide the whole time evolution into R slice or R segment. Then in each segment, we apply different strategy of the approximation, like a first order product formula method, we implement the evolution A and B. For the second order product formula method, we implement the evolution for A and B and then A. And for the high order product formula method, it can also be defined recursively. Okay, And in the series of Chilton error paper, the author showed that for the general piece order product formula method is spectral norm error as worst case error is upbounded by the t to the power of p plus 1 over r to the power of p times the operator parameter is alpha com. This one is the summation of spectral norm of the nested commutators. Okay, this is the result for the worst case error analysis. Here in our work, we show that when we consider the average error analysis, its upbound is also the t to the power of p plus 1 over the r to the power of p, but times another parameter. This one is tp. This one is a summation of the Frobenius norm of all kinds of different nested commutators. Okay, as a comparison for in the worst case error analysis is the spectral norm of all kinds of nested commutators. That's the difference. And here we only give the asymptotic scaling for this upbound. And for in the first order and the second order product formula method, we also gave a concrete prefactors. And in the previous theorem, we showed that all the summations are out of the Frobenius norm. But here we could make some summation in the Frobenius norm. They can help us to tighten the results. Okay, and for all these results, we first estimate the error in one segment, then using the triangle inequality to bound the error in long time evolution using the triangle inequality. That's why we call it a triangle bound. And the error will grow linearly with the number of segments. Okay, so the remaining problem is how to estimate this different parameter T1 or TP, and what's the difference between the spectral norm and the Frobenius norm? How big this gap could be, right? Let's say a simple example. At first, the spectral norm is greater than the Frobenius norm according to their definitions. And then if the operator say it's just a Pauli operator, like it's a Pauli X operator, then the two norms are the same, no difference. But if this say is a summation of different kind of Pauli string, like it's equals to the summation of xi times xi plus 1, then in the trace of c times c dagger, we totally have the n square terms. When the I equals to the I prime, this polystring is identity. So its trace is the dimension. But if the I doesn't agree with the I prime, then this is a new polystring. This polystring is trace is 0. So only this first part, I equals to the I prime case, makes a contribution to the total trace. Let's make the difference. And as a consequence, in the spectral norm, this of say it's a ON, but in the Frobenius norm, it's just a square root of n, because we also have a square root here, right? It's square root of n. Let's make the difference. And according to this observation, if we consider the nearest neighbor Hamiltonian, and then for this lattice Hamiltonian in the general piece order product formula method, the alpha commutator in the worst case is linear with n, On. But in our average case, this parameter TP is just a square root of n. So we could have a quadratic improvement with respect of the parameter n here. Let's say some more concrete numerical results. We consider following Hamiltonians. This is a Hexenberg model with the random magnetic field. And we fix the evolution time t, and we cited the epsilon, and we want to know the minimal required number of segments or required Chiltern number to achieve this accuracy. In our numerical result, you can see that the empirical average case is much better than the empirical worst case, the different scaling. And according to our triangle bound theoretical predictions, this scaling can match our empirical result very well in the second order product formula method. But when we consider the first order product formula method, you can see that there's a huge gap between the empirical result and our triangle bound. So this implies that this triangle bound is improper here, and the error doesn't accumulate linearly with the number of segments here. And here we also tested the total error. According to the triangle bound, the error should be the square root of n times the t squared over r. If we fix the number of qubits n and number of segments r here, the error should be the t square according to the triangle bound. But in our numerics, we find that the error is at first linear with the t, but after some threshold, it's become t cubed. And so in the following, we will give a refined error analysis. It's called interference bound. We consider the destructive error interference between different segments. In this refined bound, the result can match here the numerical result very well. It's at first linear with t and then become t cubed. Okay, in the following, I will give a more formal expression for this interference bound. We will consider some special case of Hamiltonians. And if the additional assumption is satisfied, then we could upbound the average error of first order product formula method. Here, compared to the triangle bound, we didn't change the scaling of square root of n. We only tightened the t scaling in this interference bound. Okay, and the similar thing also happened in the worst case error analysis in the destructive error analysis interference paper in 2020. They showed a similar thing, and here we use the similar techniques with them. Okay, after this revision using this interference bound in the numerics, the interference bound in orange curve could match that of the empirical result very well. Okay, this is the result for the nearest neighbor Hamiltonians. And we also consider more general case like the k-local Hamiltonians. It's a lot of terms, each term act on at most k qubits. And we give a general result for the average performance for this type of Hamiltonians. The result is related to some new induced norm here. I don't give a detailed expression here. But I will give a simple example here. If all the term is the spectral norm is bounded by 1, then we find that for the k-log Hamiltonian first order and second order product formula method, the worst case error analysis is the error scaling is n to the power 2k minus 1 and n to the power 3k minus 2 respectively. But in our average case error analysis, we could both have the n to the power k minus 1 over 2 scaling with our reduction here in both cases. Okay, and here we didn't show the result about the scaling of t and r because for both in the worst case error or average case error, they're all the same. They're the same. So we didn't change this parameter t and r. We only changed the scaling of the n, the number of qubits here. Okay, and we also consider some power law interactions. For this type of Hamiltonian, it's a kind of two local Hamiltonians. Its spectral norm for each term is related to the distance of two sides on the lattice. We mainly consider two types of power law interactions. One is infinite range power law. It's alpha equals 0 case. It means for two sides far away from each other, they still have the interactions. In this case, both the first order product formula method and second order product formula method, we both have a square root of n error reduction. But in another type, the rapid decaying power law interaction is a very large alpha. In this case, a symptotic scaling for the error compared to the worst case, we don't have the error reduction. They're the same. They're both the ON. And we also test this result in some numerics. We consider the following Hamiltonians power law interaction, also with the random magnetic field. And in the infinite range case, the first order and the second order curve, the result can match the empirical result very well. And in another case is the rapidly decaying case. The second order also very good prediction, but for the first order results, there's also a clear gap between the empirical result and our triangle bound. So this implies that maybe there's also error interference here in this case, in this rapid decaying power law case. And we didn't show it, but this is a very interesting open problem. Yeah. Okay, and here at last we considered an interesting example about out-of-time correlators. So this one is we want to know the two commuting local observable A and B. And the B is after the time evolution, it becomes a kind of BT. And this observable can be measured using the following circuits. Is that we first prepare the state in the initial state in this way, and then make the evolution. And then at last make the measurement on the first qubit. Here for this evolution, maybe we have to use some algorithm like product formula method or Taylor method. And then here we will have some algorithm error here. In this case, the input state is kind of phi tensor identity. You can understand as you fix the first qubit, then the randomly chosen the other and minus one qubit randomly. Then its mixture is phi tensor product identity. So we can use our result in the random input over subsystem case. And using our analysis, we can have a different degree of a gate reduction in different product formula method. Okay. At last, I want to give us a brief summary of our results. We gave the general result for average performance in the Hamiltonian simulation. We consider different kind of algorithm or Hamiltonians and show the distractive error interference, and also extend our result to some application about OTOC problem. And in the future, we expect that our result can be used to quantify the error with the random input in imaginary time evolution, or maybe can also be used for the partition function estimation, because they also have a trees here. The techniques should be similar. In the proof, our result, in the proof, we first use the call chain inequality. So maybe if we didn't use it, we will have a tighter bond. And another interesting question is if we also consider the fixed observable or random observable, we also expect to have a further improvement. And we also expect to see more interesting application about the random input over the subsystem or subspace. Okay, that's the all of today's talk. Thank you very much. Thank you for listening.
Yeah, thanks Shi for the talk. So there is a question by Robin Kotari. He's asking that, so in the motivation section, you said that it would be interesting to focus on the case when the input state psi is efficient to prepare, say by a poly-psi circuit. Do you know any result for Hamiltonian simulation in the worst case for such input states?
For this worst case, I guess that we don't assume the input state. We only consider the specific type sighting for the state of some unique initial state. Okay. Yeah, for the worst case, we don't assume the initial state. They are the worst case. Could be any state. But for the specific sighting, we could consider different kind of state or easily prepared state, some other different assumption about state.
I was also wondering, so in these last plots you showed for the power law, it was very strange that there was a big error. These error bars are very large for small n.
Yes.
Why is it like that? Because it seems like for small n it should be somehow better.
I think for small n, both in power law case, we have a very large variance, because here we kind of choose different random magnetic field. And both in this power law case and near neighbor case, the small number of qubits, we both have the large variance. Yeah, it's the same with the worst case, I guess. So it's not the unique phenomena in the average performance.
Do you know, is it also possible to adopt these methods sort of, like, wouldn't it be even better if you, instead of random states, if you had like a fixed state, or I don't know, like a few candidate states that you're interested in?
Yeah, I think it's a very interesting question. It's like we may give some additional assumption about the initial state, like for example, the random state in the low energy subspace. Yeah, we also expect to have some further improvement in this case, but we still haven't have a very good result for this one. It's a very interesting future directions and worth further exploration.
All right, yeah, I think it's time to wrap it up. So thanks for the talk, and we'll have to go to the next session.
Okay, thank you very much.